minus alpha b squared over 2, okay, which positive. So most of the time, if you say the interactions were this, which, okay, you shouldn't necessarily believe, but that will argue that the chi parameter should always be positive, and it's 0 when the objects are the same, and it's sort of, it's maybe a way to help you think about these interactions. Okay. Okay, so I forgot to give you any exercises, so let me give you one exercise. Using, as I said, using this as a pairwise additive interaction is not right. On the other hand, in many cases, and we saw some cases where it didn't work, it gives the right answer. The things that are more or less insulators, it typically works. At least roughly works. And so, and we saw that if I had two half spaces separated by a distance d, that the let's say the pressure between these two surfaces went something like a constant, which I'll just write as some mess, a over d cubed. And I said, this is what you get by summing pairwise interactions. And I said you could work it out. I just did it by dimensional analysis. But as an exercise, if you want to make sure you understand this, do this, instead of making these half spaces, make these two thin films of thickness t. And then what's the answer? So that's an exercise. You can work that out. You can also do it by dimensional analysis, sort of. But, just to check that you know how to do these things. Is the problem clear? You know, so in Maha's language, this will be times some function of t over d. Okay, and so at the end of the day, I was talking about the interaction between, again, these two metallic half spaces, or conducting half spaces, separated by d. And, yes?
Sorry, is the scaling still wrong for this example question?
Is the scaling what?
Is the d cubed still wrong for this?
No, I didn't say the d cubed was wrong. For it, it's right.
It is right for this?
Okay. Or almost right.
So without Lipschitz correction.
Huh?
Without Lipschitz correction.
Yeah, so I'm not doing that. That's for it. This is for non-conductors. That's for non-conductors. For conductors, we saw that there's a problem because the energy interaction diverges if I have infinite objects, because the polarizability of an infinite conductor diverges. Okay. So, and that's the Lipschitz problem. I call it. And the classical way to do this is simply to treat these two blocks of conductor in equilibrium at some temperature T, in equilibrium with the media that is that mediates ElectroCoulomb interaction, mediates electromagnetic interactions, which is the electromagnetic field, which is the radiation field. So this is the case of black body radiation, and I'm not going to give a black body radiation, but so those of you who don't have a physics background, maybe this is a little strange, but so I won't belabor it. I'm going to avoid it in some sense, but I'll need it anyway. Is that, so if you have black body radiation, then the electromagnetic free energy. See, these are conductors, and when I say these are perfect conductors, I mean that the electric field is zero. These are textbook conductors. The electric field is zero at all frequencies of wavelength. Okay, that's what I mean by a perfect conductor. Then nothing happens in the conductor, because there's nothing there, electric field is zero. Everything is what happens outside. So outside is here and on the other side. Okay? And then, if I want to know the free energy of the system, I have to write down the free energy associated with the electromagnetic fields. And if you just turn the crank, which I'm not going to do, of statistical mechanics, this is temperature, kT, times the sum over Q. Q is a wave vector, the wave vector of the electromagnetic waves, of the logarithm of twice a hyperbolic sine of h bar omega of Q over T. Omega Q is just a dispersion relation for electromagnetic radiations. If you're in free space, if you're in some kind of dielectric material, you might have some index of refraction, which I'm not going to worry about at this point. Okay. And C is the velocity of the light. Okay. So the only place that the conductors come into this problem are fixing the boundary conditions which fix the allowed wave vectors, allowed momentum. Okay, so this is just like, let's just say this sentence. So this is just like solving electromagnetic waves in a waveguide. It's a typical undergraduate physics problem, electromagnetic waves in a waveguide. Yeah?
Quick, embarrassing notational question. SH was up there yesterday too, or last time too. What does that mean?
Hyperbolic sine.
Oh, okay.
How do we do? S-I-N-H.
Yeah.
Is that the way you write it?
Yeah.
Okay.
Cool. Thanks.
That's not standard anymore?
That's the,
Huh?
that's the n plus a half?
Yeah. That's where it comes from. I think so. I think, yeah, I think it includes the half. That includes the half. Okay. So the boundary conditions that you have to apply, since the electric field is zero, if I look at the electric field, it has to vanish at the surface. So the electromagnetic modes that are allowed are those that have integral numbers of half wavelengths. Okay. But what's important here is that the long wavelengths are excluded. Any long wavelength in that direction, the longest wavelength that you can have is 2 pi over the separation of the matters. So when you use that and turn the crank, and I'm not going to do it, you find the result of modulo numerical constant that I don't remember, that the pressure between these two surfaces, I wrote it down last time, is again a number. That's a number, which of the order of unity, but you remember, could have 2 pi's in there. H bar C over D. Okay, and I want to explain that a little bit better. So now that's done for this perfect conductor. If you want to do it more generally, then you have to remember that this material has some dielectric function, which modifies this, which is a function of Q and omega. And this stuff in here, that's the vacuum, also has some dielectric function. And that changes the spectrum of the waves and the boundary condition. And then if you want to read what happens, you go look at Abrikosov, Gorkov, and Jalovsky, and you look at it, and your first impression is to throw up. This is disgusting. Okay? But so it gets disgusting very fast. Okay. So you, I mean, I'm not recommending that you do that. Okay, now you might notice,
So one quick question. For the first case here, for the electric, it's attractive or repulsive pressure? You have a minus.
it's always attractive. Always attractive, there's a minus sign. It's always attractive. And as we'll see, that you might say that some kind of real material, which is not an ideal conductor, but still maybe a little bit of a conductor, might be something in between these. Okay? And so by looking at that, you can see that there's some parameter which you might define, I'll call it C, which is just the ratio of those, which is something like A D over H bar C. There's some parameter which is maybe a useful parameter. I'll get back to that later. Where A is some kind of molecular, related to some molecular polarizability, the way I wrote it here. Okay. And the densities of the materials. Okay. So let me tell you another way to understand what's going on here, which is much easier, physically easier, at least for me it's easier, which many people have independently come up with. Leo did it, I did it independently, but the only place I've seen it written down, this kind of argument, is a few years ago in a few papers by Joe and me. So if you want to read this in any written form, the only place that I know it's written is in some papers by Joe, and you can find them if you Google his name. Okay, I forgot where they appeared. So the argument is a little bit the following. It says, if I think of again, I'm going to think of an ideal conductor. I'm only going to do the ideal conductor. In a radiation field, in a bath at a certain temperature, there's a radiation pressure on the conductor. You can calculate that. Again, in any undergraduate electromagnetism courses, you calculated the pressure by knowing the electromagnetic stress tensor, or you could do it, which I rather do it, by kinetic theory. You just say that if there's a photon of wave vector q impinges on the surface, it's reflected if it's a perfect conductor. There's the angle that the photon comes in. Each photon carries a momentum h bar q. That's the momentum. So there's a change in momentum perpendicular to the surface, change in momentum, which is 2 h bar q cosine theta. Right? Now, in this medium, you have photons of all q's. This is a black body, and there's a number of q, and that's the Bose-Einstein distribution. It's 1 over, I wrote it down, e to the h bar omega of q over t minus 1, plus a half, plus 0-point motion. Okay. So that's the number of photons with a wave vector q. We know that. Somebody else solved that problem. That's a little bit like doing here. And so you know by kinetic theory, therefore, there's a flux of particles. Each photon moves at the velocity of light. So if I want to calculate the total pressure on the surface, just by treating kinetic theory of photons, that pressure I could write as a sum over all q's. I'll just replace the sum by an integral. So I think I have a 1 over 2 pi cubed. let's say, dq, by mu, I just mean the cosine of theta. I have a change of momentum, 2 h bar q mu, that's a change of momentum. Then I have the flux of particles, the particle, each photon moves at the velocity of light. There's a number, n of q. And then I have to integrate over all q's, so it's something like q squared dq du. I'm integrating over solid angles. Okay? And you could check that I think, let's check that it has the right dimensions. Let's check the right dimension. I'll just on the side here, check dimensions. Energy, h bar is energy times time. Mu is dimensionless. Q is 1 over a length. Well, I have a q cubed. I have a q to the fourth. So I have 1 over a length to the fourth. I have c, which is a length divided by time. Right? I have energy per unit volume, that's pressure. So this is, at least has the right dimensions. Okay. So this is kinetic theory calculating the pressure. And if you do that with this black, that'll give you the radiation pressure. But that's not what I want. I'm interested in this problem. So what's happening here is that I have this radiation pressure from the backside pushing on these surfaces. And there's radiation pressure here pushing the other way. But there's less radiation pressure here because some of these modes are missing. The long wavelength modes are missing. That's just, remember when I talked the first day about depletion interaction. It's the same thing. So this is depletion of photons. And let's see what that gives. Question?
I don't know what is the mu in your equation.
U is just cosine of theta.
Okay.
So the integral of that is 1 or something. I'm not worrying about numbers. Okay. So therefore, I'll rewrite this thing here, that the pressure, in other words, this pressure is negative. Obviously it's negative because I have pressure coming in from the outside and there's less in the inside because I don't have long wavelength modes. Okay? They can't fit. Okay? So what I have is that the pressure is minus this integral, 1 over 2 pi q. And roughly speaking, let's write it. Let me first do it at high temperatures, at finite temperatures. I'm not going to worry about 0-point motion here. I have h bar. I'm running it q cubed. The integral over d mu gives me 1 or something like that, or a half or something. I have c dq, and then I'll put in this e h bar omega q over t minus 1. Okay. Now, and I want to integrate this from q's of 0, very long wavelengths, to something like, let's say, pi over d, or 2 pi over d. I'm not worrying about being sloppy about factors of 2 now. Okay? Because those are the modes that are excluded. You get it? The long wavelengths don't exist because I have this boundary condition. Yeah?
Why do you also not consider the non-integer modes that are also excluded?
You mean the 0-point motion?
No, well, this may be the naive question, but in between the first mode and the second mode, there's, a continuum of modes.
No, the boundary condition on the electric field is that it has to vanish at the surface.
Right.
So there only are, in that direction, there only are integer and half integer modes.
Right, but outside, like on the opposite side of this infinite.
The other side, so that's why I'm minus it. I'm saying all those other things cancel to a first approximation. That's my point.
He's worried about why you don't do a sum, you do an integral rather than a sum.
Oh, okay, if you want to be careful, you do a sum. But this is good enough. Good enough for astrophysicists.
No, actually, I think I was asking about this stuff in between, in between the first and the second mode. Like, you don't have those modes inside the slit, but you have them ostensibly outside.
Outside, yeah. So they're pushing on this side. I'm only looking at the stuff, that's why I write it minus. This is the stuff that's missing.
Phil, the question is that outside you have all modes, not just integer.
Yeah, I have all
And
modes.
also the high frequency modes as well.
Yeah, that's right. So that's
why
right.
don't you include the high frequency modes pressure from outside?
Yeah, that's why I'm only, but all the high frequency stuff is the same to a first approach. Almost the same. Almost the same. Okay? That you can convince yourself. So the major thing that's missing is this. Everything else is essentially the same. And you can just do that by replacing these sums by integrals, which is good enough. So there might be slight corrections, but they'll be very small corrections.
So I don't understand what modes outside, what's the outside?
Okay, so what I wanted to think of is that you really have some huge cavity, which is thermostated at a temperature, and I have these two blocks of stuff. So there's these things are being, so let's treat them as spheres if you want. So there's pressure on the outside and there's pressure on the inside. Now, I want you to think that. So there is stuff on the outside pushing because I'm assuming I'm in equilibrium. Is that what you want?
Yeah, I was thinking these were...
Yeah, so they're not really, there's stuff on the outside even though they're effectively very large.
Okay.
Okay, so this is the main stuff that's missing. Okay, so because we're only excluding the long wavelengths, if I look at the argument of the exponent, it's h bar c q over t. But in this integrand, the biggest this could be is pi over d. So if the temperature is bigger than h bar c over d, right? If the temperature is bigger, then this argument is very small, right? I mean, I could imagine be very large, and then this is obeyed, right? If that's obeyed, then I could expand the exponent. The h bar cancels, the c cancels, 1 power of q cancels. It becomes very simple. This becomes like minus 1 over 2 pi.
That's the equivalent.
Cubed times the integral of q squared dq. The c cancels times kt from 0 to pi over d. So this is in the order of minus t over d cubed. Okay. And I'm not going to write down the numbers. Okay. Interesting. Oh well. Oh, here it is. Okay. Okay, so it's of order this. So this suggests, by the way, notice I'm getting back to this d cubed, but it's not a, it's kt. Okay. So this suggests that for perfect conductors with a large separation, this is a completely classical limit. There's no quantum mechanics here. These are, right, there's no h bar, no hint of h bar. These are purely thermal fluctuations. And it gives rise, notice that it doesn't depend upon anything. It only depends on the distance between the surfaces is completely universal. That is, any materials, anything will have that. And this is a long-range attraction. But what about this condition?
It says it's T times the number of modes that missing.
Huh?
It's just T times the equal partition, right? T times the number of missing mode.
This is a dimensionless number. It's just a number of pi's and 2's. There's nothing
No,
else.
no, I'm saying the whole result is just temperature times the number of dimensional, number of modes.
Yeah, but so before, in the old result, it was A. Is that what you mean?
No, I'm just saying the whole expression is just equal partition. That, in that limit, you're getting equal.
Yeah, that's just, yeah, equal partition. Yeah, so in some sense, and this is, by the way, this kind of result is very typical. So notice that there's nothing here even about the radiation field. You could have had, so this kind of result occurs for all, any kind. So here I did a particular case of the radiation field. Suppose there were some other fields. Suppose there were springs and stuff in between there. I would get exactly the same answer because there's nothing in this that tells you what anything else. This is a completely universal thing. Things always attract at long ranges with T over D cubed if there's any medium fluctuation in between. So this is completely universal and in that sense completely empty of anything interesting. It's useless, but it's always there. Things always attract at high temperatures. Okay, now, what is this temperature? Well, here I know the numbers. If this is room temperature, I know what H bar is, I know what C is. When does this fail? And if you put in the numbers, which I did, I forgot what it is, I think you find that this is only good if for D about 10 to the minus 3 centimeters at room temperature, which is pretty large distance, okay? So, and mostly we're interested in shorter distances than that, okay? So we're usually not in this limit, okay? Yes, sir?
I have a question. So it seems like that you assume that the modes that are parallel to the walls are also damped.
Didn't quite hear you when you said.
So in this result, you assume that the modes that are parallel to the walls are also damped. Right?
The ones that are parallel, for the wave component of the wave vector parallel to wall could be anything.
Yeah, but
I'm integrating
you
it.
have the integral over.
Yeah, but I'm just cutting it off because I'm using spherical coordinates crudely. This is crude.
Yeah.
But at the answer, so that's why I'm not worrying so much about the numerical prefactor. All that does is fiddle with this numerical prefactor.
There's a cosine there, but when you integrate cosine, it just gives you a number.
Well, but it's, yeah. You have to integrate the cosine. That's not serious. Okay, so what happens if this condition is not obeyed? In other words, where I can't do that. So let me, instead of doing it in general, because it's obviously messy, let me go immediately to the limit T goes to 0. If T goes to 0, then this gives you nothing, and then I got to remember that there's 0 point motion. There's a half, and the Bose-Einstein energy is nq that I wrote down plus a half for each mode. So in that case, as T goes to 0, this integral becomes minus 1 over 2 pi cubed. The integral, this stuff gets replaced by 1. So I have h bar c q cubed dq, which gives me obviously something of the order minus h bar c over d to the 4th. Right? This is 0 pi over d, okay. So this is the Lifshitz answer. I wrote it down somewhere. You see, you get the same thing. Okay. So this is the classical limit. This is the quantum mechanical limit. Okay. And that convinces me that this is probably a good way to think about this, because this is obviously much easier than doing any of this stuff. Now, okay, you may have to worry about doing the sums properly and all that stuff. You can do that. Okay.
Phil, do you need anything outside? If there was no outside pressure, you would still, because integrals are
You need the outside pressure. This is the minus. This is what's missing.
But that's just
This
a
is
constant.
what's not balanced. This is what's not being, the rest of it is being balanced. This is the unbalanced pressure. Just like depletion interaction. I have the osmotic pressure from the inside, and I have nothing on the inside. So here it's the same thing, except it's not nothing, I just subtract out a piece. That's not balanced.
Isn't it just a constant of the...
No. It depends on the thickness. If it's very big, I don't have anything excluded. If it's very little, I have a lot excluded. It's not a constant. It depends on the wavelength. I mean, that's the nice thing about this. Okay. So the way I like to look at it, this is just depletion. Now,
So what happened to your exponential factor in the limit?
Huh?
In the t goes to 0 limit, what happens to your exponential factor?
well, that diverted 0. So really what goes here, I didn't write it correct. This thing here is really, should be nq plus a half. And this is nq. And when t goes to 0, this is e to the infinity for any q not 0, which is 0. And all I have is the half. So if you want, I have a half, another half. I was cavalier with the numbers. Okay. Okay, now you could go a little bit further if you want to. Well, let me give you an exercise. What do you think happens if these two conductors are like this, or thin films? It's another exercise. Thinking about it this way. And the way I want you to help you think, let me make a suggestion. Okay, so if you didn't like this, you're gonna hate this. But okay, I'll do it anyway. So the way I'd like you to think about these kind of real materials, not these ideal conductors, is that you have both an A due to the polarizability of the atoms, but yet there may be some free electrons around, so you have some electronic polarizability. I mean, associated with the free electrons, which is like a metal. So they both coexist. Obviously, if the films are very thin, then the polarizability, at least the polarizability associated with electric fields perpendicular, may not be infinite. And so you may have some combination of this kind of stuff and that kind of stuff. Okay? And that's very hard to work out, but let me make a suggestion. Let me make a suggestion in the pure quantum limit. In the pure quantum limit, just to begin, because you see there's complications here. You have quantum mechanic fluctuations, you have thermal fluctuations, and then you have boundary conditions. It makes it messy. But you might say that really if I had two conductors in this geometry, but these were not such great conductors, that at some short distance, remember, this is the short distance behavior now, because conductors, that I would have some pressure, disjoining pressure, or joining pressure, I guess, negative disjoining pressure, h bar c over d to the fourth. But let's say that, that for some reason, the velocity of light, I could turn it, crank up and make it be very, very big. If the velocity of light is very, very, very big, remember this a over d cubed was the limit of infinite velocity of light, no retardation. So you might say that there's some kind of interpolation formula, which I'm not deriving, I'm just writing down, dividing this by 1 plus some parameter, I'll call it some constant k, times this thing which I call c, I'll write it h bar c over a d. Let's suggest that. So now, if c goes to infinity, I can forget this, the h bar c cancels, and I get pi going to minus a over d cubed. And the other limit, c goes to 0, that's 0, and I get this. So this is some kind of zero temperature interpolation formula which tells you, suggests how things go. So this would be the very, very short distance behavior. And this would be, this 1 over d4 would be the longer distance behavior. And then if you turn up temperature, then you get another crossover at long distance to this classical minus 1 over d cubed term. So it goes as d cubed, d fourth, d cubed. That's what I think was what happens. And you could see what thinks about what happens for the case of thin conductor terms in this kind of context. Okay.
Your constant a there has dimensions. Right?
Huh?
Your constant a in your psi has dimensions. So what's the physical meaning of that constant?
Well, it's just, I just took it, the ratio of this constant here, the k.
Well, in your extension parameter.
Yeah, this is dimensionless. This is dimensionless. That's dimensionless.
No, but there's distance, h bar and c, but you need something else. You need
No, this is dimensionless. This is energy.
okay,
That's
so,
energy times time. That's length, right? This is dimensionless.
and energy comes from what?
A is the Hamilton constant. It comes from atomic energies. This is all quantum. Everything here is quantum. A, remember A is something like alpha squared, atomic polarizabilities of the objects that are in the material, times the square of the density, the number of atoms per unit volume, times an electronic energy. This is like a volt. Okay. Yeah.
So this interpolation, is this just ad hoc to match?
Just ad hoc.
Okay. You're just
Just
matching-
purely ad hoc. I said it's got to match, so that's the way I can do it. It's no physics in that. This is how would I do it. Maybe you can figure out how to do it. I mean, or figure out something that's right. I actually tried a little bit and I couldn't figure out how to do it right. But anyway, but there's a few important points here. One is illustrated by this. Here, we worried about the electromagnetic field, and these are everything in this so-called van der Waals or Casimir force comes from fluctuations of the electromagnetic field. And there could be quantum fluctuations, low temperature, or thermodynamic fluctuations, okay? And you see how they give different results in different regimes. But this field that's fluctuating could be any field. So for example, if I have some kind of polymer network with objects in a polymer network, there will be fluctuations that will do the same kind of thing. If I have a membrane with you'll hear more about membranes from Shmulek, Safran. You'll see that if particles are in the membrane and the membrane has fluctuations, they will give rise to forces between, say, proteins or pores in the membrane. So, and they will all look the same way. Yeah, by the way, the d cubed has to do with 3 dimensions. If you were doing it in a membrane, I think it has to go like 1 over d to the 4th or something. But you know, I think it goes, the distance dependent goes as 1 over d to the 4th. This number here is purely come from dimensionalities. Okay.
Phil, one more question, sorry. There, your crossover was based on temperature on the right board.
Yeah.
Here you're doing it, there is no T anywhere.
Here I'm not doing the t. Here I'm doing a crossover with regard to
This parameter.
d. Well, d is parameter.
And T should not be, and that is.
No, I'm only doing it at t equals 0 because t makes it more complicated. So if you want to do them all at once, be my guest, you have to fiddle around a little bit more. It's a little more complicated.
The second crossover is due to T.
The second higher crossover is due to t.
So
This is only a t equals 0 thing. It's just a quantum thing, just to show you how you can imagine it works.
And so even for very, when you have 1 over d cubed, you think that at 0 T you have this attraction?
Yes. Yes.
The-
If
the
the
electric-
conductors are not perfect, yeah.
So it's not fluctuation, thermal fluctuation.
No, these are quantum fluctuations. This is H bar. A has H bar in it. This is quantum fluctuations, not thermal fluctuations. This is all quantum, T equals 0. Okay. So that's the about all, but all these fluctuation things look, in some sense, the same. And they're all complicated because they don't have pairwise additivity, that makes them complicated. And often they have this caution or retardation. Okay, so these things are very complicated, and in some sense I'm doing bad because I'm starting with the more complicated stuff. But in the sense of being complicated, in compensation, they always exist. They're always there because there's always some field around to interact with. Okay, so these things are always there, and you can't get rid of them. And notice, at this level, between identical objects, they're always attractive. And that's something you know, you should learn. In all of soft matter, all interactions, essentially, if you think about it properly, lead to attractions. The only thing that leads to repulsions is entropy. Only entropy leads to repulsions. Okay, so I'm going to erase all of this because I want to change gears completely. So much for this stuff. And what I said I would do in the second lecture, and I haven't started yet, is talk about electrostatics. So electrostatics ought to be a breeze compared to this, because electrostatics is freshman E&M, and it should be very easy, but of course, it's even harder than this. Oh, I didn't tell you, by the way. This stuff, but nobody asked me. To what extent is this stuff checked? And the answer is very little. Okay, there are very few experiments which actually give rise to any details of this. I think there was a conference at the Institute for Theoretical Physics in Santa Barbara a few years ago about experimental aspects of this stuff, and there were lots of, I gather, I didn't go to, but there were a lot of arguments and stuff. And what I understood from the people who were there, that the result is that all the people who see they observe it experimentally are full of shit. that was the message, that they're not observed. So because these are all weak forces, hard to observe, so there are no systematic experiments to check any of this stuff. Okay. There are some analog systems, but they're only analogs.
What about, you studied membrane inclusion?
Pardon me?
You studied at some point inclusions in membrane and their attraction? What about in those?
Well, but those are analogs, they're not exactly the same thing, because then they involve a different field. It's not the electromagnetic field.
Right, not only, but some intermediate.
Even those are not checked.
Really?
I mean, there are things that are consistent with them, but there's no systematic probes. I mean, you could say, oh, I see something, so it must be this. But there are no systematic studies, as far as I know. But this is, trying to understand this experimentally is a very hot area of research these days. So there are people trying to do it, but I just think it's not there yet. You know, obviously with all our ability to do these very nanoscale experiments gives you a chance.
How much harder if you have something in between your, like in soft metal typically you have a third media in between.
Yeah.
That messes everything up, or is it?
Well, as I said before, you've got to put in the dielectric function of the stuff in between.
So that's not a big change.
Okay, so that's a good point. So I gave you this kind of depletion interaction way of doing it, and I didn't tell you all of it. Which is this something? I'm not sure. Leo, is this what you did more or less?
Yeah, basically.
So one of the experts in this field of fluctuation forces is our friend Meron Kardar at MIT, and he says that this depletion way of thinking about it is not right. And he says he thinks it's not right because if I don't do it for Lipschitz, he agrees for this ideal Lipschitz case to give the same answer, but if you do it with a medium in between, when you put in real dielectric functions, that you don't get the same answers as are in AGD, okay? And now he just says, I don't know that he checked it, I think he just said it because he doesn't believe that it is. So that's a good exercise. I once asked some graduates if they wanted to try to do it, but nobody I found was interested in trying to do it. Because you could imagine doing it this way, but you have to solve the electromagnetic waves, you have to, in both medias, and match the boundary conditions, and it becomes a lot of work, okay? But I think it's conceptually doable. But then the boundary conditions are more complicated. So Meron, who's the guru for this field, says this way of thinking, he thinks is not right, but I sort of like it, that's why I told you.
Did he ever tell you what his objection?
Pardon me?
Did he ever try to articulate his objection?
I couldn't hear.
Did he ever articulate his objection? What doesn't he like?
He didn't, we didn't talk that long about it. He just said, oh, I'm sure it's not right, huh?
He didn't like that he didn't think of it first?
But I mean, I would take what he said seriously. Because he says, okay, so electrostatics. I'm not going to finish the electrostatics today, but we'll start. Okay, so the strongest interaction that we have in soft matter is electrostatics. It is just a Coulomb interaction. It's the strongest thing there is. And so if things are charged, that's going to dominate over everything else. Okay? So when are things charged? Well, you know that things are charged when they get ionized. And things ionize, for example, salts when they dissolve in water. So most of the time when we're talking about electrostatic things, most of the times in soft matter we're talking about in water. And I don't want to say a lot about water, but I'll have to say a little bit about it. Okay. So one of the properties of water that's important for electrostatics is that it has a dielectric constant. Dielectric constant of water is about 80. And so at room temperature, it's again questions about temperature dependence. Its dielectric constant is temperature dependent a little bit, but as you'll see later, the dielectric constant in any theoretical stuff that we're going to do always comes in the form of a charge squared over epsilon kt. Okay, and epsilon T is approximately constant. Because after all, water is, you know what water looks like. This is oxygen. I'll make it, I hope there's no chemists in here because they'll be sick when I write this down like this. But, okay, but it's a little dipole like that. And therefore, it has a dipole moment which could orient in an electric field. And just from orientation of a dipole in an electric field, at the first problem you work in statistical mechanics, you see that the dipole moment in electric field is proportional to 1 over the temperature at low electric field. So epsilon T is a constant. Okay, so that's that's a good thing to remember, that between freezing and boiling, this product changes by a few percent. It's essentially constant. So you'll see a lot of formula that will look like this, but don't think that that implies any temperature dependence. Okay. So that's the most important property of water. It has high dielectric, and therefore there's dielectric screening. So if you remember, and we're always talking about using units that Noah used, CGS units, that the potential between two charges, let's say, is E squared over epsilon R, right? Or let's say Q1, Q2, with a sign. Okay. And if so I have this screening, this interaction is reduced when you put an object in water, roughly speaking, by a factor of 100. Okay? And that's good. So let's imagine that I have something like sodium chloride that I want to put in water. And of course, you know that this wants to become sodium plus Cl minus, because by transferring, this is just atomic physics, an electron from sodium to chlorine, both ions now are closed shells. So they're stable, very stable, okay? So therefore you would like to have this. So if I think of sodium chloride as a sodium ion and a chlorine ion held together by Coulomb interaction. And so that energy is minus, because they're different signs, E squared, if there's no water, E squared over some atomic size. I mean, a hardcore size. So A is like, this is like an atomic energy. This is of the order of electron volts. Electron volts is huge compared to thermal energies. Sodium chloride doesn't dissociate in a vacuum. Okay. But if I put it in water, I divide by epsilon by 100, and then this is maybe like, goes down, this is maybe 10 eV, this goes to maybe a 10th of eV. KT is about a 40th of an eV. So this is, by putting it in water, you're getting closer. Closer to the fact that entropy can make these ionized. Still not too close. But then you have to look a little bit closer. Unfortunately, water, well, not unfortunately, or fortunately, it's the way it is, water is not just a dielectric medium, it's made up of these kinds of molecules. And these molecules also have charges. The chemists would say they have partial charges. I'll be a stupid physicist, so I'll just think of them as O double minus protons, okay? Like this, okay? And then, if I put an ion, like let's say let's say this is sodium plus, then what actually can happen, and does happen, is that the water, this is the oxygen, will like to, this O double minus would like to get in, snuggle in pretty close to the protons, to the sodium, and form a very rigid layer. Now, of course, to do this, it has to do something with the structure of the water, and water, as you may know, this is something, that's why it's complicated. The cohesive energy comes from a hydrogen bond network of water, and we'll talk about that tomorrow a little bit, okay? But, so how this happens is a little bit mysterious, but the net result is that this ion becomes much bigger. Instead of having a size A, it has, these waters are very rigidly attached. It could be several layers. And there's a new size B, which is bigger than A. So this layer of hydrations, if I come back, get this A replaced by B, which could be 2 or 3 times A, and then I'm starting to be in business. Then I'm getting energies which are very much in the range of thermal energies. Okay, let me finish it. So, and the main reason that salts dissolve in water is not so much because of the high dielectric current, it's part of it, it's because of this effect which is called hydration. Okay? This hydration effect is understood at the level which I've drawn pictures, but is not understood very, very deeply here. And one of you guys, if the guy is working with Phil Geisler, who worries about this kind of stuff, but it's very controversial. And I'll get back to that tomorrow. I don't want to belabor it, but it's hydration, for the most part, that's driving the dissolution. It's hydration coupled with the dielectric constant. The dielectric constant is not itself sufficient. Okay?
I was going to ask about entropy. You know,
KT means entropy.
No, I know, but you're suppressing entropy of water.
When I do that.
Right, but
So I have to do, that's why I said this is tricky. I have to do it, I have to do this. This is a separate problem to calculate this hydration layer. I'm killing rotational entropy, and I may be breaking hydrogen bonds, and I got to do it, and it's a separate problem. But it happens. We know that. Okay. There's plenty of evidence of that. Okay. There's no doubt. There's plenty of spectroscopic and chemical evidence that this happens. Okay.
but the driving forces to make sodium and chlorine ions more stable to get closed shell, or what's the driving force?
Well, the first, no, this part is to drive the ions. And to get the ions to separate is entropy. But the entropy comes because you force them to be far apart because they'd much rather be surrounded by waters of hydration. So there's water that gets in between and doesn't let them get close together.
I mean, so you're increasing their entropy, but you're giving up
absolutely, it's all entropic, yeah.
You're increasing their entropy, but you're giving up entropy of water.
You're losing some entropy of water, so it's a balance of entropies, absolutely. And that's, I would say, it's not understood in detail. It's very controversial. And I'll get back to that a little bit tomorrow, if I have time. I don't want to talk about it here, I just want to say, let's accept that's what happens. And then so really what happens is they're hydrated, and then they dissolve. Okay, so now, is that okay? I mean, and remember, yeah, so the low temperature state of the system is always molecules stuck together. Because at the end of the day, it's the attractive electrostatic interaction which is the dominant thing. Is this clear or is it mysterious? I mean, I don't expect you to understand the details of that because I didn't explain them. Because we don't know. Okay, obviously we know something. Okay, so now, given that so now I want to talk a little bit about salt solutions. Really, I'm sorry, I missed a central point. The reason I want to study electrostatics, because, I mean, I sort of told you, we have a lot of systems where it is in water. In fact, all the biology exists in water. So, and because biology exists in water, everything involves charge systems, okay? And the reasons why things dissolve in water is often because they gain entropy by dissolving, and that's usually like this, like what I talked about for salt. If I look at, for example, our famous biopolymer, DNA, as you know, is a helix of sugars. Each base, remember there's bases that are coming here, each base, the distance between base pairs is 3.4 angstroms. Each base pair has 2 phosphates. So that means as far as linear charge density is concerned, if all the phosphates ionized, when you put them in water, phosphate is a strong ionizer like sodium chloride, you would have 1 negative charge every 1.7 angstroms along its length, okay? Now, let's not think of DNA like that. Let's think of DNA, I want to think about surfaces. So let's think of DNA, as we heard from Michael, as a cylinder whose radius is like a nanometer. And if I have 1 charge every 1.7 angstroms along that cylinder of a radius of a nanometer, that gives to a charge per unit area. Think of it as a surface area of a cylinder of about 1 charge per square nanometer. Let me write that down. That's an important number. So I'll call it surface charge density sigma, 1 charge per square nanometer. That's DNA. About that. And DNA is almost the most highly charged molecule known to man. There's a few others a little bit higher charged, but they're all about that. If I look at another example, an inorganic example, if I look at mica, mica is a clay. It's a clay, it's an aluminum what's it, some kind of aluminum oxide. But it has, if I look at the surface of mica, it's bristles with potassium hydroxides. Put it in contact with water, the potassiums go up, and if you just count how many hydroxides there are per unit area, I'll give you one guess. It's about the same. Okay. And as we'll see, this is sort of the limit. You can't get anything higher than that. And we'll see why. Okay. So what I want to understand is what's the nature of interactions between surfaces whose charge densities are in the range of 1 charge per square nanometer. Okay? That's what the object of a lot of people's thinking about for a long time. Okay? As it turns out, this is a very high charge density. I mean, high compared to what? I'm not telling you yet, but it turns out this is sufficiently high that it causes trouble. Okay? Or if you like. So that's where I'm going with this. But before I do that, I want to tell you about the simple theory of this stuff, of salt water, which is the Debye-Hückel theory. Because if you understand the ingredients of the Debye-Hückel theory, then I claim all the rest of it is easy. Okay. So the Debye-Hückel theory, we all learn in freshman chemistry. Unfortunately, they teach it in freshman chemistry, so you don't learn anything about it because you're not ready to learn it, and so you don't. If you remember anything about it, you probably remember the wrong thing. So I'll try to remind you about the Debye-Hückel theory, okay? And that'll probably take the rest of the time. Okay, so we want to look at what happens when I put salt, a little bit of salt in water. it dissolves. It's this horrible hydration stuff here, but I'm going to say, okay, I don't understand any of that stuff. It's too hard. But we'll just think of it. I have these. At the end of the day, I have these small ions. They may be hydrated, but at the first approximation, I'll treat them as small, as small objects. And I want to look at low concentrations, and the concentrations become small. And I will worry about that. So the way I want, so if I have, I have basically a plasma. I have a beaker of water with these ions in there around. I'm going to assume that the concentration is small enough that everything is ionized. I don't have any unionized salt, and that's all I got. Okay, and I'm at some temperature. I mean, this is soft matter, so I'm never at the ground state. Obviously, this is not the ground state because it's entropy that makes this dissolve. So I want to understand the electrostatic aspects together with thermodynamics, because I want to know about thermodynamic quantities. So the one thing that we believe in life are Maxwell's equations. Okay, and the appropriate Maxwell's equation here is just that the divergence of the displacement is, again, in the correct units, is 4 pi times the charge density. Okay, so that's it, and we're going to do it. You know, we're thinking of water, so we have we'll treat water. We'll do what do they call the primitive model, where we treat water not like this, but just like a dielectric continuum. We'll do the simplest thing we can. So the only property of water is essentially a vacuum with a dielectric constant of 80. Okay, that's the model. So this becomes minus epsilon times the Laplacian of the electrostatic potential is equal to 4 pi times the charge density. Okay. Now, in freshman electricity courses, this is the standard problem you solve. You might not write it this way, but you're given a set of charges, and you're asked to calculate the potential or the electric field. That's the canonical problem, right? That's every problem in first year E&M is doing that. Unfortunately, that's not real life. In real life, there's nobody. We don't have Griffiths around to tell us where the charges are. Okay? We don't know where the charges are. And the charges are governed where they go. It depends on the electric fields. So we have a self-consistent problem to solve because we don't neither know rho nor phi. Okay, so we're stuck. Okay, so we can no longer turn our crank. So this is the canonical many-body problem. This is, in fact, E&M is the canonical field theory. All field theory comes from electromagnetic fields. Is you do mean field approximation. And you say, okay, I don't know where all the fields are, but I just say that each charge is distributed with a Boltzmann distribution, because I'm at a temperature T, around the average potential that comes from all of the other charges. Mean field. This is not exact, this is an approximation. And it's a lousy approximation, usually, but it's the easy, because what it does is, since it says each charge sits in the average potential to all the other charge, I'm converting a problem which is many-body problem of 10 to the 23rd particles to one particle in a field. And one particle in the field is the only problem I know how to solve. Okay? So you convert an impossible problem to a doable problem, but you're paying a penalty because you don't know what errors you're making. You're making errors, okay? But let's do that. So that says that rho of r in this approximation is some, okay, there's two kinds of things. There's anions and cations. So it's something like some constant rho plus e to the minus e phi over kt. This is a Boltzmann distribution for the cations, for the sodiums. And then I have, let me call this C plus. Concentration, I'll put a charge here. And then I'll have minus for the anions, e to the e phi over. Okay, so this is an approximation. So rho, C plus and C minus are just, if you like, Lagrange multipliers to assure that I have the right number of molecules in the system. Okay? And this is an approximation. This is mean field. This says this is the potential at the position of any particular ion. Okay. But okay, mean field. So that in physics, whenever you have a many body problem, the first thing you do is solve the mean field problem. So that's what we do. We try to do here. And then you worry about if it's right or wrong. So just plug that in here. Clearly, if phi goes to 0, C plus and C minus have to be the same. So for this particular problem, I can put this in here, and this becomes 4 pi, some constant, I'll call it C0. I have E, and then I have 8 pi, something like the hyperbolic sine. Oh, I should write it euro. Hyperbolic sine of E phi. Huh? Okay? Is there a minus sign? Maybe a minus sign. Okay, and now it's convenient to define a dimensionless potential, E phi over T, because that comes in there. So if I just use that, then I can rewrite this as del squared phi is equal to some, I'll put all this stuff in constants. This is just, I'll call it kappa squared, hyperbolic sine of pi. So now it looks very simple, where kappa squared has a dimension of 1 over a length squared. Kappa squared is A pi C0 this quantity here, which I define as L. This is called the Bjerrum length, and it's the characteristic length that tells you about electrostatics, or if you like, electrochemistry. For room temperature, well, I told you that's a constant. This is a number, and it's, I don't want you to take it too seriously. So roughly a half a nanometer. Okay? That's what it is. So that's just putting in numbers. Yeah.
I didn't understand, you made a comment about in freshman chemistry, you do this and then you don't really understand. What context is this done in freshman chemistry?
Well, in freshman chemistry, you never have to worry where the charges are. They tell you the charges here, there, and there to calculate the potential.
Right.
But here I don't know where the charges
So
are.
that's freshman E&M. But you said you learn about the biology.
Well, freshman chemistry, you learn about the Bi-Hugel theory.
Really? Okay.
Usually, yeah. I learned it.
I don't remember.
Well, that's why it's worth doing. Okay. So, okay, this is not quite right. So this is already, this is an approximate equation. It's approximate. Far from being exact, but it's already horrible. It's a second order, nonlinear, partial differential equation. Nonlinear. So, forget it. So, I mean, this is what Maha talked about. I mean, but the first thing you do when you see a nonlinear differential equation, if you're a physicist and you don't know anything else, you linearize. Right? Because we know how to solve linear partial differential equations. So let's linearize. Linearize means, in some sense, the potential being small, then you can linearize. Small potential. I don't know what that means exactly, but I'll tell you a posteriori, this corresponds to dilute systems. That's why I said I'm talking about dilute systems. So this is good, and you'll see it's not that great, but it's okay. So let's linearize. We have a few minutes. So if I linearize, this is del squared phi, this is kappa squared phi. And kappa squared, now C0 was a Lagrange multiplier, giving you the right concentration. But now, if phi is very small, it means everything is weak. It's essentially a homogeneous solution. So C0 is just the concentration of salt. It's how many molecules of salt per unit volume I've dissolved in there. So that's a quantity that I know. So kappa squared now becomes 8 pi Cl. Kappa squared is 1 over a length squared. The inverse of kappa is called the Debye length. I know people now don't like to use that. They want to use a different narrative. Because Debye was a bad guy. Okay.
No, apparently he was not bad guy.
Oh, he was not a bad guy?
He is good, so
Okay, so we can still use it. Okay. And so let me tell you what this number is, because I always like to remind you about numbers, that if I have 1 millimolar salt, 1 millimolar salt concentration, then this length is about 10 nanometers. Okay? Yeah.
A very quick question. How do you go from rho to C0? What happens with C plus and C minus?
Oh, because they have to be the same, because if I go to phi equals 0,
Right.
with the potentials, and it has to be that I'm putting in, it's just from charge neutrality. I'm not putting in ion, I'm putting in molecules. So
Right,
I have,
I understand
that's
that.
charge neutrality.
But if it's charge neutral, then why the right hand side is not 0?
Oh, it's not 0 locally, it's 0 globally.
Some way you have a potential or something.
Yeah.
Create something down.
If I'm sitting on a charge here, there are potentials around it.
Okay.
Yeah.
I mean,
Yeah.
in principle, that C plus C minus could have some smooth variation on phi, and some weak dependence on phi, right?
At the end of the day. But right now, at this level, it is none. It's just a still concentration. Yeah, bunch of questions.
I think for you define kappa squared as C times L. Or what
Where?
was it?
Here?
Yeah, what was the L?
L is not L. I'm sorry. E squared over epsilon. So L,
Oh, okay.
whenever you want to see, in this language, whenever you want to see an electrostatic interaction, you need an L. L is the electrostatic, it's the measure of the strength of the electrostatic, okay? Is E squared over epsilon T. It's a half a nanometer. Okay? There was another question?
You made a point of mentioning that when the concentration was small, C naught was just the false amount of salt.
Yeah.
Why is that not
Oh,
true?
because what I've assumed is that the potential is small everywhere. If the potential is small, it doesn't do anything.
Yep.
So everything is distributed around, it's like the limit of no interaction, perturbation theory.
But why wouldn't C naught still be the amount that you would dissolve even at high?
Well, I just called C the amount that I dissolved.
Oh, I see.
It's no longer has to be solved self-consistently, it's just a constant. That's all I'm saying, in perturbation. Okay, now this equation is easy to solve. Okay, so imagine, we have to take an origin. So let's say I have a sodium, a cation at the origin, and I ask, what's the potential around that? I could just as well have chosen something else. I could have chosen an anion, okay. And then the solution of this equation, like, by the way, like all differential equations, you don't solve them, you just know the answer. Okay, then you check. So the solution of this equation is L over R, e to the minus kappa R, where I assume that this is a point charge. I'm assuming this is very small. Okay. And you could check Laplacian in spherical coordinates is 1 over r squared d by dr of r squared d by dr. And you put this in there and you see this works. Okay? And the boundary condition is such that when kappa is very small, this is just a Coulomb interaction, L over R. That. And it falls to 0 at infinity. So this is it. This is the solution for a point charge. Okay? Is that okay? You could plug that in, check. Okay. And this is what everybody remembers. What is this telling you? It's telling you that if I put a positive charge at the origin, it's attracting some negative charges, and the negative charges are a little bit closer here than they would be on the average, and the positive charges are a little bit further away, and it means that if you go out to a distance 1 over kappa, the Debye length, the result is that if I look inside, I see something that's essentially neutral. It's essentially neutral, and the electric field, or the potential, is dying out to 0. I mean, that's the physical meaning here. The positive charge is attracting some negative charges, blah, blah, blah. Okay. Now, what's important in thermodynamics is not this. I have 3 minutes. To do the important part is the energies. I want to do the energy. So I could do that pretty fast. What you remember from electrostatics is that the energy of a charged particle in a potential due to other charges is 1/2 the charge, I'll always use E, times the potential at the site of the charge. The potential at its site, the origin. Okay. That's, again, that's freshman electrostatics. Okay? So in this case, if I want to get the energy, I have all the positive charges and all the negative charges. But here I'm clearly assuming everything is homogeneous, so all positive charges are equivalent. All negative charges are equivalent. So this is 1/2 E phi times C. Phi at the positive charges minus 1/2. This is what I'll call phi positive. E for the negative charges, phi minus times C. Per unit volume. This is the energy per unit volume. But I have a problem. And the problem is that phi at the origin where the charge is what? See the problem? Nobody?
Divergence.
You have divergence. Okay, it's infinite. Okay, so this is all point charges, all charges have infinite, very large self-energies. This is, if you like, the high ultraviolet divergence of quantum electrodynamics, if you want to be fancy. Okay? So that infinity, what do you do with that infinity? You can't control it, so you just subtract it out. You say that infinity is essentially 0. You just replace infinity by 0. In other words, I'm just redefining my 0 of energy. Okay? So I don't worry about that. Let me look at this. This goes, I'll write this as short, but I want to know what happens near the origin. So I do a Taylor series expansion of the exponential. So this first term diverges It's a self-energy, but it's a self-energy of a charge which I don't care about. It's nothing to do with any physics. I subtract it out. The next term, R times 1 over R cancels. I get a term minus kappa L. All the other terms, when R goes to 0, go to 0. So then this term here is approximately minus kappa L over 2 times C. This term is exactly the same. This is a minus, but I have that minus. That's what the energy is, approximately. Okay? Energy per unit volume. So I could write that in the following, but CL is related to kappa squared. So this is just minus KT kappa cubed over 8 pi. Okay, that's what I get. Now, let's look at this and then I'll be done. So this is important. First thing, this energy is not a mean field energy. This is what the field theorists call one-loop correction. This is a fluctuation on the mean field energy. Because on mean field energy, all the anions and cations are distributed homogeneously. So if I look at any small volume of space, it has equal numbers of protons of sodium and chlorines. The electrostatic energy is 0. So in mean field level, the energy is 0. This energy here is a correction to mean field, because this is a fluctuation correction. In other words, this is one loop. And that's why, and this is what's the Bi-Hookel theory. So Bi-Hookel theory is not purely mean field theory, it's a linearized mean field theory with a one loop correction. So it's really a piece of approximate stuff, okay? But the important thing here is that since kappa squared goes to C, this is proportional to C 3/2. So it's not like a virial expansion. It has this funny 3/2 power, and that becomes because Coulomb interaction is long range. It's a complicated, horrible thing with two signs of charges. It's horrible, okay? And the net result is that I don't have a virial expansion. I have the first correction. This is a low concentration, goes to C to the 3/2, and it's negative. That's negative sign is unambiguous. Now, you could think of this another way. Once you realize this is a fluctuation correction to a problem, first thing you know, fluctuations always lower the energy, because if they didn't lower the energy, they wouldn't exist, so it's always minus. It's sign you know. These are thermal fluctuations, so you know the energy scale is kT. This is a problem of asking for the energy density. So I need a volume. This is an energy per unit volume. The only length in this problem that we've defined is kappa. So the answer has to be minus T kappa cubed. It can't be anything else. The only thing I don't know, the only thing I did the calculation for was the 8 pi. Everything else is God-given. You have to know. It has to be. Okay? This is Allah Mahadeva. Purely dimensional analysis, it's got to be like this, okay? Well, dimensional analysis plus understanding that this has to be thermal fluctuations. Okay, so you're forced to this. Now this is very important, and we'll talk more about it next time. The reason it's important is that notice that this is an energy which is lowered as the concentration gets higher. That means that the energy is bigger when you have a higher concentration. When the ions are not being repelled, this is an energy which is attracting the ions together. This wants to condense. This is the interaction that enforces Earnshaw's theorem, which says that all neutral systems want to the ground state, if they're classical, they condense to a point. Okay? The only thing that works against this is entropy, the entropy that we started with. So if I look at the free energy density, I have to add to this the entropy of the plasma. I have a two-component plasma. I have the C pluses and C minuses. So I have an entropy, I'll just say it, is 2 log C per ion. So an entropy density is 2 C log C. We know all about the logs. So the free energy is this at low concentration plus the entropy term, and these two terms fight against each other. And all the physics of electrostatics plus thermodynamics has to do with the fight between those two terms, okay? And so we'll talk about that tomorrow. And I'll try to talk about it fast so we can talk a little bit about water.
You said only one scale involved in one more topic. Variables of zero.
Yeah, but the dielectric, it doesn't appear in here.
Yeah, but in Mach's terms.
No, it doesn't. It's not a relevant length because this is what defines the problem.
If I know this formula, then
Yes, yeah, but I'm saying